as managing director of Merlot. So I'm not teaching. However, I do see all the emails that my colleagues at the university get. And we have a faculty development center at my university, which I helped to start. And I see the kinds of courses that they're offering, training courses to faculty with regard to educational technology. And just last week, I saw a course being offered on the use of scantrons. Now, my university is very advanced in terms of e-learning and so forth, but they're still using scantrons in order to grade student performance, which I'll talk about also in a few minutes. Now, let's look at the second half of the 20th century. And let's look at it from our perspective, a computer-based perspective. And I think in the view of some, that's kind of a myopic view. Here is another view of the history of educational technology, and I'll read this to you. And you see the reference. Technology is commonly thought of in terms of gadgets, instruments, machines, devices. Most educators will defer to technology as computers. Tell you a side story. When I was heading up the Faculty Development Center at my university, we did faculty training in the summertime, and we were teaching them how to use Blackboard and WebCT, and I can't remember anymore what we were teaching them. And I had this revelation. I said, you know, they're using this tool, but they don't know what the background is. They don't know anything about preparing instructional objectives, for example, and some other things I'll talk about here. We should offer courses in developing instructional materials and so forth, rather than just show them how to dump materials into a learning management system. So we offered the first course, had this kind of turnout. I wasn't teaching that course, fortunately. After 25 minutes, this faculty throughout the university, multidisciplinary, within 20 minutes or so, there was a revolution. You don't have to teach us how to teach. We know how to teach. We want to know how to use Blackboard. We only want to know how to use the tool, because we know all there is to know about how to teach, how to develop instructional materials, and so forth. So this, of course, that's untrue. But nevertheless, most educators consider educational technology as to do with computers. And if you were to ask them what is the history of instructional technology or educational technology, this is the kind of thing that they would come up with. So again, I'll say that there are many different views when you talk about the history of anything. There are many different views of what that thing is, depending on also many different aspects where So let's look at educational technology from our standpoint. Now, I hate to say it, my roots are as an electrical engineer. My graduate school is all in educational theory, but it's hard for me to remove the electrical engineer from my view of instructional and educational technology. So let's look at hardware as it relates to us. And remember that when it comes to learning management systems or any other kind of instructional software, we can't do any of that stuff unless there is first hardware. Now, hardware in our field actually started with this perennial challenge that we have in education. The screen is shortened here, so I wasn't sure you were seeing it all. So I'll give you a second to look at this cartoon that I found. And it has to do with sort of the lifelong problem that we as educators have, the need to test our students. And I'm going to talk about testing also in a few minutes, a little more about testing. From an educational instructional technology standpoint, this is probably the first machine that really falls under the umbrella of technology, hardware technology in education. I should ask this question. It's a hard question to ask such a big audience, but nevertheless, how many people here are faculty? Can you put up your hand, please? And how many are instructional designers? Lots of all. Among the faculty, how many are, let's say, in history? Oh, good, I can say anything about history. Math? Nobody? Engineering? Really? Engineers never come to these kinds of things. Science? Okay. What did I leave? Psychology, social sciences? And who didn't I mention? That's a given. We wouldn't be sitting here. We wouldn't be sitting here if we weren't educated. A lot of you are in the faculty or college or Department of Education? Yes? Okay, so you'll know a lot about this stuff. Okay, good. Anyway, this was the first device that we can actually put under the umbrella of devices in educational technology. And it had no lasting effect. The real thing here is that it was the first box that we were able to use in an instructional setting. But then in the 40s and the 50s, we had some people who came along with some outstanding theories of learning. One of them, of course, was B.F. Skinner, and the other one was Norman Crowder. And they both had theories of learning. The Skinnerian, I'm not going to go into all of Skinner's, the Skinner box and all of that, but there was a development of something called the linear program. It was predicated on operant conditioning, and it was, you present the learner with a little bit of information, and perhaps there's a little question at the end of the stimulus, or of the treatment, or of the subject, and the student constructs a response, constructed response, and then turns the page and goes to another page. There was no processing of the student's response. It was simply page after page after page. Crowder had a different theory. This diagram is a little bit illustrative of his theory. It was called branching. And you can see that although Skinner's was based on a psychological perspective, if you like, Crowder's was based on a communications perspective. Now, in a Crowderian branching learning environment, you present the students with a large chunk of information, and the student is then asked a question based on what was in the question, and it usually was multiple choice, and depending on the choice the student made, he or she was directed to turn to page this or that or the other thing. And this gave rise to programmed instruction and programmed instruction manuals. And these little diagrams are meant to illustrate the difference between the physical programmed instruction manuals of the day. And I used programmed instruction manuals. How many of you have ever used a programmed instruction manual? Some. The linear ones were thin. They took you through, depended on how the instruction was designed, 30 or 40 pages of material. But the branching one, because there had to be material and a response for every selected item that the learner made, and turned to page such and such and page such and such, branching program instruction manuals were very much more thick. So the theory behind both of these things was quite different. In 1954, we invented teaching machines. And the teaching machines, across the top you can see the Skinnerian, or the linear kinds of teaching machines. And on this top right quadrant, there is a learner who's presented a little bit of information. Is there a laser or something here? No. And you can't see the mouse. Maybe here. Oops. Top right-hand corner, you can see there's a little field that presents the learner with a little bit of stimulus, and then a place for the constructed response. The constructed response was not processed at all. When the learner pressed a key, went to the next frame, and just continued. On the bottom, you can see two different kinds of Crowderian or branching teaching machines. Students have their options to push a multiple response question. And you can see that the screens are much larger than on the top, because there were larger amounts of information that was presented to the students before they were expected to make their response. So that was fine. But also in the 1950s, actually it wasn't fine. They were crummy machines. But nevertheless, it's what we had in the 50s. And these were pioneering efforts, and they led to other things. In the 1950s, and I'm using the 50s generically, of course it was in the 40s and the 50s, that we had the emergence of digital computers. And here are some pictures I found in the archives of of mainframe computers. These things are a whole mess of different kinds of computers. But the thing that's characteristic about these kinds of computers, the early kinds of computers, is only one person could use one of these machines at a time. And of course they were huge, and some of them used vacuum tubes and so forth. But in the 1960s, we had some late 50s, early 60s, we had some really breakthrough concepts in software that made a huge difference to where ultimately we were going to go as educational technologists. First of all, the stored program concept shown here really came in the 50s, but nevertheless it became popular. What that meant was you could write a program, an application, and run an application on a computer, and if the application had to do with physics, well, then you were running a physics application. If it had to do with instructional technology, you could dedicate the computer to whatever that instructional technology application was. But that wasn't very practical until we invented I'm generically calling them time-sharing systems. We, meaning we in the world, invented them. They came from different places, of course. Time-sharing systems meant that we could take one of those big boxes I showed you in the previous frame and the notion of stored programs, and then many people could use a big, expensive computer all at one time, each one of them running their own kind of application. Very important to where I'm about to go with instructional technology. So that meant, for example, a physicist could be running his or her physics analysis. Someone could be running, well, I was going to say semantic, but we didn't have some of the things that we can do today. One could be running a computer-assisted instruction sequence. One could be running whatever, all apparently at the same time. Oops. This allowed us to move, I'm going to show you some of the evolution here, allowed us to move from these electromechanical teaching machines to computer terminals. And that's a teletype. That's the first kind of computer terminal that we had in time-sharing systems. And by the way, I hate to admit this, but I lived through much of this, used these kinds of things, did these kinds of things, both when I was an undergraduate electrical engineer and then later when I got into education working for Canadian General Electric. It allowed us, the stored program concept allowed us to expand the Crowderian branching situation beyond that into more complex branching. So you could write a program that asked a student, a learner at one of those kind of terminals, a question. You could make very complex kinds of programs, branching from here to there to everywhere. As I mentioned, the programmed instruction manuals that were branching kinds, the manuals, those things were huge because, as I said, for every question, you probably had to have 5 different answers, and it all had to be physical pages. But anyway, you could code that sort of thing and make the response processing in the stored program much more sophisticated than just turn to page this and turn to page that. Another thing that happened later on in the 60s, and I was working at IBM when we started to do this kind of thing. We dumped those terminals, those teletype terminals that pounded out things. Anybody here ever use a teletype? You remember 10 characters a second? It was awful. You just sat and you waited and you waited and you waited until when you watched the thing pound out whatever you were waiting to pound out. Anyway, towards the end of the 60s, we started to see the replacement of these hard copy devices as terminals, and they began to replace them with cathode ray tubes or CRT displays. Then in the 1970s, we saw and late 60s actually, started some really interesting things for us. All of this stuff, all this technology, led us to be able to develop customized multimedia computer-assisted instructional terminals. And I've picked the 3 that are sort of the seminal works that were developed at that time. There are others, but these were really well known around the world. First of all, there was this Plato system that was developed and worked on. It was developed by CDC. I can't remember even what it stands for. I don't think they're in business anymore. And notably at the University of Illinois, and Carl Bitzer was the principal investigator, if you like, who became world-renowned for this multimedia terminal that was Plato. Plato no longer exists. Plato morphed off into a different kind of company. Nevertheless, this, and has anybody here ever used the Plato system? Yeah, me too. One time, I was at the University of Illinois when I was at IBM looking at this system, and I wound up playing Snoopy and the Red Baron with somebody somewhere in the world, and I got so involved with this dumb little game, I almost missed my airplane. The IBM 1500, how many people have heard of the IBM 1500? Must be almost as old as I am. The IBM 1500 was a dedicated machine, a system that was developed by IBM, and there were a limited number of those things made and used around the world, under 100. This was a system design. It was built on IBM standard components, but it was designed and tailored for the use of computer-assisted instruction. And I'll show you the difference between these two things in a minute. Seymour Papert at the time, in the 70s, probably earlier, invented the programming language Logo. It's quite a different kind of thing, but I don't think you can talk about instructional technology development in that era and not mention Papert and Logo, the programming language, and this turtle, which was a little device that rolled around the floor with a pen over a piece of paper, and students could program Logo to draw designs, tell the turtle to go forward and rotate so many degrees and so forth, and draw pictures on the piece of paper. Later, that transferred from the physical turtle on a piece of paper to a virtual turtle on the screen. This in part, there were these things at the top were part of customized multimedia computer-assisted instruction systems. Now, on the left at the bottom, there was this system that never got a lot of notoriety, and it should have. It was the MITRE system, and it was built by Data General. It was a customized instructional technology computer-assisted instruction system. There are two architectures. On the left and on the right was the architecture for the 1500, IBM 1500 system. And let me tell you what the differences were. With the IBM 1500 system, all the multimedia devices, and there was multimedia, there were slides, and there were graphics and so forth, all of the devices were situated at the terminal, at the CRT. It wasn't a CRT, but at the display, the 1500 display. So if there were images and so forth that were going to be displayed, the devices were attached to the terminal. Whereas in the ticket system, which stood for Time-Shared Interactive Computer-Controlled Instructional Television, with the ticket system, all the devices were situated at the server. And the communication out to, it was a standard television set. All the communications, all the images and the video and so forth out to the terminal were on a standard NTSC, North American Television Standard, a television signal. So it's quite different. With the IBM 1500, it was sort of distributed multimedia. With the ticket system, all the stuff was there at the server end. Anyway, those were the customized CAI systems of their era. But in the 1980s, finally, we came up with what I'm characterizing, and I'm sure you've heard called affordable computing. And I'm not going to go into what's Moore's Law too much, but essentially Moore's Law says that every 18 months or so, the power of an integrated circuit chip doubles, and the cost stays about the same. There are different ways you can play with the ratios, but nevertheless, because of Moore's Law, we're able to put on a smartphone or a tablet or so forth, the kinds of power of computing that I showed you with those big, huge boxes that were in the 1950s. And this led us in the 1980s and onward to this kind of stuff. So everything we can do today is thanks to Moore's Law. Now, there's no question that having standalone devices so you have a standalone device, you can program it, but really all the developments of networking and Ethernet and so forth, TCP/IP, and everything that we can do today has enabled us to have the internet and the World Wide Web, without which we would just, we would have come to a dead stop probably in the 80s. So, while all of this stuff was going on in the world, and if you were in the computer industry, as I was, there were other things that were going on. Educational technologists were quietly and hard at work doing what we do best. We were creating a community of educational technologists. And we evolved all that teaching machine stuff into formal bodies of knowledge. And that's from the 50s. Now, I got my master's in 1970 and my PhD in 1973 and in 1972. And it's just so dramatic and remarkable how we have become a community of educational technologists, how we've evolved over those, I don't want to say how many decades, but I told you. So we've developed a formal bodies of knowledge. We have ontologies. We have conferences like this, journals, societies, etc. We never really had this stuff before. If you went to an American Educational Research Association annual meeting back in the end of the 60s, the early 70s, as I did, what we do today was a special interest group, and they kind of hit us around the corner in a dark, dusty place, and we talk to each other in very dark rooms. So we've really, really come a long, long way. We've taken many of the tools and the things on the left-hand side that you see. These are the general kinds of things used by computer scientists and IT application developers and so forth. And we've taken those things, extrapolated them, and we've built for ourselves sets of tools and et cetera, to enable the kinds of things that we all do in our teaching with technology. And we even built open education repositories like Merlot. And you'll notice the little asterisk up there. So I'm not going to talk about repositories too much, but this is my blatant placement ad. Today, you know that if you watch a television and you'll see some guy driving a Buick or a Hyundai or something, even though there's no ad for the Hyundai or the Buick, when he pulls up to the crime scene, there's a shot of the front of the car that's bigger than the screen. That's my shot of a Hyundai or a Buick or something for this presentation. So we've created an international e-learning community, and until very recently, I don't think the whole world has known that even exists. But recently, the world has come to know that, in fact, there is a community that we're all a part of. And this is the second half of the presentation that I'm going to do. And I really do apologize. I'm going to read this. And the reason I'm going to read it is, as I said when I started, this, in my mind, for me anyway, is a work in progress. I'm having different ideas and thoughts as I go along about where we're going and what could be next. So what I'm going to now talk about are some of the technologies that I think the world, I'm pretty sure, I know that the world is looking at that will have a dramatic effect on where we're going next. And you're going to ask me a question, right, Helen, at the end? So, it's impossible today to talk about the future of instructional technology without addressing the phenomenon of, can you guess? Or perhaps, as I think it should be called, MOOC version 1.0. Currently, most supporters of MOOCs are politicians and university administrators who believe that MOOCs are a solution to the rising costs of education. Then there are all those venture capitalists and companies who fantasize about seizing some of that $18 billion US spent annually in the United States on e-learning in higher education. But most of those who might become responsible for developing and delivering MOOC-based instruction are not quite so enthusiastic, and sometimes wonder whether MOOCs might be just another instructional technology fad. But it's pretty clear that everyone is a long way from declaring victory regarding their stance on MOOCs. As an instructor and educational technologist, I think that it's right to be wary and even critical of the current rendition of MOOCs. And that's because they are built on what I consider to be a faulty instructional technology construct. If you think about it, a MOOC is really just an online course offered to a lot more people than usual on a scalable version of a conventional learning management system, or LMS. If you really think about the construct of MOOCs, you might realize that these platforms have little to do with learning and mostly to do with teaching. They really should be called teaching management systems, because that's what they do, and to enable an instructor to collect, stage, and present content to students. There's really very little inherent functionality in today's LMSs to allow an instructor, or even the LMS itself, to know if the student is learning or not. The instructor simply gathers what he or she thinks are effective learning materials, perhaps including tests from a test item database, or perhaps some other kind of assessment tool, organizes all this in chronological order, usually based on a course syllabus, and then populates the LMS with this content. Someone informs the registered students, usually by email or through a college catalog, when the course is about to begin. MOOCs are predicated on this very same model. The main difference is that the course is advertised and open for a larger audience than the usual pre-selected registered college student. From our experience teaching conventional online classes at various levels of education, we know that students must be self-motivated to complete a college-level online course. Students who are not, or who are not self-disciplined, are rarely very successful. Consider, for example, that most pre-college students do more poorly in online courses than do more mature seniors or graduate students. It's no surprise that when we open an online course to a worldwide student body, all of whom have no real investment in completing the course, that we see reports about dropout rates in the order of 90% and success rates even less, at less than 3%. One of the main differences between today's MOOCs and conventional online courses, aside from the scalability of LMSs, and by that I mean the ability, the advertised ability to handle tens of thousands of students, is the inclusion of improved social networking tools. These tend to go beyond the ordinary threaded discussions used by instructors in contemporary online classes to stimulate discussion that would otherwise take place in a classroom. MOOC social networking tools are designed to allow students to discuss questions or problems with one another, mostly because it's impossible for a class of tens of thousands to be easily supported by just one or a few instructors. Who's my student here that is probably following really closely? But going back to the architecture of MOOC LMSs, and if we consider the history of instructional technology, we can see that the current model of LMS-directed online instruction is hardly different from a hybrid version of B.F. Skinner's and Norman Crowder's linear and branching models of programmed instruction. For example, LMS-based, listen to this, because this was a revelation that I had. For example, LMS-based online courses expect students to read or somehow interact with the content, then do some kind of assignment or test, then move on to the next chunk of content. In fact, this model isn't even as good as Crowder's branching model because the next chunk of content presented to the learner is not dependent on the student's assignment or test results. It's simply a modified version of Skinner's linear model. But LMSs, like the electromechanical teaching machines of the 1950s, are limited by the technology of today. Let's look at the future generation of MOOCs. There are emerging computer and instructional technologies that can do a much better job with online instruction in MOOCs than what we're doing now. It's likely that one day these technologies will be integrated into our online methodologies to enable greatly improved future generation of MOOC LMS architectures. Architectures that will rely really and focus on learning rather than teaching. Using adaptive learning methodologies, a true learning management system can in real time know a great deal about the learner and present the learner with different content or instructional modalities based on that knowledge. If you think about it, this is really a 21st century rendition or extension of Lee Cronbach's and Richard Snow's seminal work on aptitude by treatment interactions. How many people here know about ATIs? How many of you education people have never heard of ATIs? That's grim. Okay, well, you've got to go back into the literature and read about ATIs. It's really, I think it's really important. That's, of course, because my dissertation had to do with ATIs. Today, unlike in the past, digital computers have the power to do many more useful things related to instruction than when Cronbach and Snow started their early work in the late 60s and early 70s. For example, today's computers can access a great deal of information about any individual's online learning profile. They can ascertain the state of the learner's progress in real time. They can also in real time access a large variety of potential treatments, and by that I mean different content or teaching modalities. And they can immediately administer the right treatment via the right medium to the learner, all of this in real time. The technologies upon which this kind of instruction depend are currently very much in the public eye. The ability to store, access, and analyze huge amounts of data in real time is a feature of the phenomenon called big data. In instructional settings, big data stores could contain data not only about the particular learner at hand, but also about thousands or even millions of other learners whose profiles may be distinguishable from a particular learner. Consequently, the computer could have the ability to not only diagnose the state of a particular learner in a particular online course at a particular moment in time, but also to apply a treatment that has a high probability that it will conform to the learner's aptitude. I brought the definition of aptitude in this context is much broader than Cronbach and Snow's original definitions of aptitude. But remember, when they were thinking about ATIs, they were thinking in a limited context based on the technology of then. We have much more broader technologies today that will allow us to think about aptitudes in a broader sense and treatments in a much broader sense. This kind of aptitude by treatment interaction, if Cronbach and Snow could think ahead 60 years, would be exactly, I think, what Cronbach and Snow ordered. I really was an advocate of ATIs and Cronbach and Snow back when I was doing my dissertation. And of course, I went away from all of that when I worked for IBM and different companies and became an IT professor. And it really, I was really saddened when I went back into the literature to learn that both of these guys had passed away in the last 10, 20 years. Another emerging technology that can enhance this kind of ATI scenario is, cloud computing. In order for true adaptive teaching and learning to take place, it'll be necessary to ensure that large volumes of big data are available for real-time learner situational diagnosis and treatment assignment. This can best happen if the big data used in the model come from many, many different data sources. Cloud computing enables the integrated sharing of data from many sources, all available when needed from one virtual data mine in the sky. Of course, this model does not consider all the privacy and security issues that are sure to cause many people significant anxiety and grief. But that's a subject for another day. For all this computing to take place in real time, computer hardware and software processing and data networks will have to provide much more throughput than we are accustomed to today. One of the driving forces in this regard is the work being done in multi-core processing, today mostly seen in the kinds of computing characteristic of supercomputers. But as Moore's law and its replacements continue to evolve, and the methodologies for programming and application development for these kinds of computers also continues to evolve, we'll one day be able to access, compute, and process the ATI data that we need to accomplish the kinds of things needed for true adaptive learning to be realized. This will be especially true and necessary if we replace our more expensive conventional user interfaces with Socrates-like robots that can do real-time speech recognition, decision-making, and speech generation in practical and cost-effective ways. Now let's talk a little bit more about learning outcomes, a subject that we traditionally dance around when we discuss the effectiveness of teaching and learning. There's no question that assessment of learning outcomes is a difficult subject. It's so difficult that sometimes we give up trying to collect objective data regarding the effectiveness of our efforts. Instead, we choose to talk about seat time, or we ask students their opinions about the instruction they've taken or their opinions about the instructors. Seat time is an irrelevant metric when we talk about online learning, because after all, where exactly is this seat that we're talking about? And should we care how long it takes for an online learner to reach a certain level of subject matter as mastery or competence? Also, by definition, opinions are subjective and don't meet any kind of standard for reporting on the effectiveness of instructional modalities. We certainly don't want the students to dislike their instructors or the instructional process, but more objective data regarding students' learning outcomes would be of far more value to us when we're trying to make decisions about how next to teach a student, a subject, a class, or a course. Over the last decade or so, with the increased attention on online learning, a number of organizations have come into being that are interested in developing standards related to the nature of content available for online teaching and learning. And they're also interested in making these materials shareable and available to the broadest audience of instructors and learners. These standards allow instructional content developers to describe their work using metadata definitions that have been developed by the standards groups. When web-based metadata are attached to a learning object, they can be more readily discovered by instructors searching for appropriate open learning objects, sometimes called OERs, Open Educational Resources, in order to integrate them into their courses. I want to tell you that when I use the word OER, it has a very specific definition. It was defined about 10 or 11 years ago at a UNESCO conference sponsored by the Hewlett Foundation. The definition of OERs has evolved, I would say degraded and degenerated over the last 10 years, but we should know that OERs have a very specific definition. Recently, how much time is there? I can't hear. Just tell me. Give me 5. I can't hear. Hey, I'm going to wrap up soon. I'm almost at the end. One of the problems with learning object standards is while they do a reasonable job of categorizing a learning object in various ways, none of the standards includes metadata definitions that describe how good or how bad in terms of learning outcomes the learning object really is. There is some work going on by the IMS, the preeminent other things, preeminent standards developers, having discussions and adding metadata to their definition of learning objects that will include metadata that describe learning object quality and the effect of learning objects on instruction. This means that the definition of learning objects, which currently has nothing in it, none of them have anything in it with regard to the quality, the relationship of the effectiveness of a learning object, will have metadata that will allow us to search for learning objects on the web, not only based on metadata that describe the level, the discipline, and so forth, but also we'll be able to have metadata that describe the effectiveness of a learning object. When all these technologies come together that I've just described, when we're able to collect online in the cloud big data, we'll be able to look and find a learning object where all of the learning outcomes data that have been collected in real time based on the experience of students who are actually learning using the learning object, we'll be able to discover those learning objects and know, based on objective data, whether the learning object really is an effective learning object, whether it's a learning object that you want to integrate and incorporate into your instruction. So let me just go to the end here somehow. I can't do that. So, let me, if I could, no, I can't do it because I don't know how to manipulate this. There are many cliches about people who foolishly try to predict the future. I have a slide here of a big monkey, especially when they look to the stars, cards, or even shards to do this. In this talk, I've looked a little bit at the past to see how educational technology has evolved, to try to give us some clues about what lies ahead. I've tried to touch on a few contemporary technologies that I think may have a dramatic impact on the future of our field. I'm sure there are some things I've omitted, some deliberately, some that I've simply neglected to consider. But it probably doesn't really matter, because who's to say right now what the future will bring? One thing that we can probably agree on is that when we get to the future, there will still be a future for us to try to forecast. My wife said to me last night that we can only hope that there's going to be a future. There are a lot of things going on in this world, climate change, and et cetera. But I'm pretty confident that after all these technologies come into being, that we will have a future. These technologies will impact everything that we do in terms of educational technology. And there will be dramatic changes in the next 10 or 20 years with regard to how these technologies